Hey guys, in this section we're looking at chemical kinetics, or what's also called reaction kinetics, which is basically a subdiscipline or a branch of physical chemistry that's concerned with understanding the rates of reactions. And so that's what we're going to look at in this chapter, chapter 12. In chapter 13, we'll deal with chemical equilibrium. As you follow along in the book, you'll see some of these diagrams. One thing that's important with chemical kinetics is obviously looking at the environmental and biological and economic importance of things that are affecting the atmosphere or how your body is metabolizing certain proteins, for instance, and also how it is economically feasible to make something like ammonia from nitrogen and hydrogen gas. In this section, we'll also be looking at catalyst. So the rates of the chemical reactions are going to be very dependent on the reactants. If you're looking at something like the explosion of gaseous hydrogen gas and oxygen gas, which you see on the left side of this diagram, that happens in a fraction of a second, whereas other reactions such as the rusting of iron is going to be occurring extremely slow. Therefore, to describe a reaction rate quantitatively, we always need to specify how fast the concentration of the reactant or the product is going to change per unit time. So you see that formula there, rate is equal to concentration change over time change. So the reaction rate itself is going to be defined either as the increase in the concentration of a product as it forms per unit time, or as a decrease in the concentration of the reactant per unit time. In our example here, we have the thermal decomposition of gaseous dinitrogen pentoxide, which is N2O5, which is colorless, to give you the brown gas nitrogen dioxide, which is a common air pollutant, and also molecular oxygen, which is also colorless. So changes in the concentration as a function of time can be determined by measuring the increase in pressure as 2 gas molecules are converted to 5 gas molecules, from 2 to 5 on the left to the right side of the equation. Alternately, concentration changes can be monitored by measuring the intensity of brown color due to the nitrogen dioxide with a spectrophotometer. So in this table 12.1, we see how the concentration as a function of time at 55 degrees Celsius for this particular reaction and how it occurs, and the changes in the concentration. Again, simply by putting it into a spectrophotometer, which basically looks at the absorption of visible light and the intensity of the color and quantizes it. Simply put, as you'll see in the lecture guide, the reaction rate, again, being defined as the increase in concentration of a product per unit time or as a decrease in the concentration of the reactant, would look something like this if you were to quantize this. This would be, again, the positive slope that you see there as it forms a product, and in purple there you see the negative slope as it decreases the reactants. Looking at the rate of decomposition of N2O5 here, we see that as oxygen and nitrogen dioxide form, we have nitrogen pentoxide just disappearing. Simply put, this would therefore be negative in accord with the negative slope of the hypotenuse of the triangle, which is defined by the change in the concentration of N2O5 and the change in time. Because reaction rate is defined as a positive quantity, we must always introduce a minus sign when calculating the rate of disappearance of a reactant. During the time period for 300 to 400 seconds, as we see here in the calculation, the average rate of decomposition is going to be equal to 1.9 times 10 to the minus 5 molar per second. And as you see here, for the specific time period between 3 and 400 seconds, the reaction rate is defined to be a positive value. It's important to look at the molar amounts that you have when you're forming something like two different products here. So as it states in the textbook, for the decomposition of N2O5, 4 moles of NO2 are formed and 2 moles of N2O5 disappear for each mole of oxygen that forms. Therefore, the rate of formation of oxygen would be 1/4 the rate of formation of NO2 and 1/2 the rate of decomposition of N2O5. So looking at that, you can see how the actual rate of formation of NO2 would be 1/4 that of the rate of formation of oxygen and 1/2 the rate of decomposition of N2O5. It's important to specify the time when quoting a rate because the rate changes as the reaction proceeds. So you're going to have a different rate if you look at the time period of 300 to 400 seconds versus something like 600 to 700 seconds. So ordinarily reaction rates depend on the concentration, but at least some of the reactants and therefore decrease as the reaction mixture runs out of reactants, as you can see in our diagram here. So what we have is the concentration of nitrogen dioxide versus time when the nitrogen pentoxide is decomposing at 55 degrees. And again, as the measurements are made at shorter and shorter time intervals, the triangle defined by the change in the concentration of nitrogen dioxide and the change in temperature is going to become smaller and smaller. And the slope of what you see here as the hypotenuse of the triangle approaches the slope of the tangent of the curve. So as we said earlier, the rate of the decomposition of the nitrogen pentoxide is going to depend on its concentration, slowing down as the nitrogen pentoxide concentration decreases. So what this looks like is you have A plus B forming your product, where A and B are the reactants and little a and little b are the stoichiometric coefficients in the balanced chemical equation. The dependency of the reaction rate on the concentration of each reactant is given by an equation called the rate law. In this equation, K is what we call the proportionality constant, which is called the rate constant. So here you see, and this is a very important point, is that the values of the exponents in the rate law must be determined by experiment. They cannot be deduced from the stoichiometry of the reaction. So as you see in table 12.2, there's no general relationship between the stoichiometric coefficients in the balanced chemical equation and the exponents in the rate law. In the first reaction, in table 12.2, the coefficients of what we see there as the organic bromide and water in the balanced equation are both 1, but the exponents in the rate law is 1 for the organic bromide and 0 for water. And so the rate law is dependent only on the concentration of the organic bromide. So in the next section, we'll see that the exponents in the rate law depend on exactly how the reaction occurs, and that is on the reaction mechanism itself. So one method of determining the values of the exponents in a rate law, or the method of initial rates is to carry out a series of experiments in which the initial rate of the reaction is measured as a function of different sets of initial concentrations. If you take, for example, the oxidation of nitric acid or oxide in air, one of the reactions that contributes to the formation of acid rain, you have 2NO plus O2 yields 2NO2. In table 12.3 below here, we see the initial concentrations and the rate data for this particular reaction. Note that the pairs of experiments are designed to investigate the effect of the initial rate of a change in the initial concentration of a single reactant. If you look at the first two experiments, for example, the concentration of NO here is doubled from 0.015 to 0.030, while the concentration of oxygen is kept constant. The initial rate increases by a factor of 4 as the initial rate here is 0.048 and goes to 0.192, indicating that the rate depends on the concentration of the nitrogen monoxide actually being squared. When NO is held constant, if you look at experiment 1 and 3, and the initial O2 is doubled, then you see that the initial rate doubles from 0.048 to 0.096, indicating that the rate depends on the concentration of oxygen to the first power. Therefore, the rate law for the formation of NO2 becomes second order with respect to NO and first order with respect to O2. This analysis can be done mathematically by just, again, observing, keeping one concentration constant, and looking at the effect of doubling the other concentration on the rate of formation. Again, because you're keeping the oxygen concentration constant and you're doubling the NO concentration, you are actually quadrupling the rate of formation, which means that needs to be raised, the concentration needs to be raised to a power of 2. Likewise, looking at the concentration of oxygen doubling, we see we're keeping the concentration of NO stable, doubling the concentration of oxygen, and we see that the rate of formation doubles, which means it would be raised to a power of 1. So again, the reaction order would be considered to be second order with respect to the concentration of the nitrogen monoxide, and first order with respect to the oxygen. And to get the overall order of the reaction, you would simply add those together. In the lecture guide, I make a big point of following the units to determine your K value. Be sure you practice the problems that are in the lecture guide for determining the units of K. So basically, if it is a 0 order reaction, we'll see that the units of K are just the concentration over time, which is molarity over seconds or molarity reciprocal seconds. If it's a first order, which means it's basically dependent on one of the say A in a reaction, then the units for K would be 1/seconds or reciprocal seconds, and so forth. Check out a more formal approach of calculating your superscripts there for your M and your N on page 452. So there is a mathematical approach as well that you can use if for some reason you're having difficulty doing a particular problem. A good practice for this would be to actually use these units and solve for your K values for each one of these different orders. So here we have part 2, which is section 12.4, where we start looking at the differences between first order reactions and second order reactions. So far all we've looked at really is the rate law, which basically tells us how a reaction rate depends on reaction concentration. But we're also interested in how reactants and product concentrations are going to vary with time. For example, in the book it reads, it's important not only to know the rate of which atmospheric ozone layer is being destroyed by air pollutants, but also what the ozone concentration will look like 20 years from now, and how long it will take for the concentration to change by a given amount, say like 10%. Because the kinetics of pollution-induced decomposition of ozone is a very complicated process, we'll consider the very first general first order reaction where A is forming a product. So a first order reaction, again, is one whose rate depends on the concentration of just a single reactant. So therefore the rate would equal minus the change in the concentration of A over the change in the concentration of T, or time, change in time, which is basically K times the concentration of A, as we see here on the top part of our slide. The integrated rate law for the first order reaction is another form of showing a rate law in which you're using natural log A sub T over the concentration of A initial concentration of A being equal to minus KT. We see here that the integrated rate law, or natural log concentration of A at point T is equal to minus KT plus natural log initial concentration of A is basically the equation for a straight line. So natural log A sub T is a linear function of time. So the graph of natural log A versus T is therefore a straight line having a slope M being equal to minus K and an intercept B being equal to natural log A sub 0. So a good way of checking to see if something is a first order reaction is basically to examine the appearance of this plot, this natural log A sub 0 plot over time. And if it forms this linear decay, as we see, then it will be a first order reaction. And a second order would look different, and a third order would look different. Again, if we want to look for the value of the rate constant here and the consumption of nitrogen pentoxide, then what we do is we plot it. And to confirm that the reaction is actually first order, we check to see whether a plot of the natural log of A versus time gives a straight line, as we see it does. Because the data points are lying on a straight line, the reaction is first order in N2O5. The slope of the line, again, can be determined from the coordinates of any two widely separated points on the line, and the rate constant, K, can be calculated from the slope. K in this case becomes 1.7 times 10 to the negative 3 per second. Note that the units of K are the units that you would expect for a first order reaction. In a first order reaction, you can also expect to see a half-life. The half-life of a reaction, which is symbolized by T to the sub 1/2, is the time required for the reactant concentration to drop to 1/2 of its initial value. So if you consider something being like A is going to form its product, then to relate that to the reaction's half-life to the rate constant, you start with the integrated rate law that you just saw. When T is equal to T to the 1/2, the fraction of A that remains is A sub T over the concentration of A initially, which is 1/2. Therefore, natural log of 1/2 is equal to minus k times the half-life. Since natural log 1/2 is a constant, we can use that natural log 2, which is equal to 0.693 over k. So you can just learn that equation as t1/2 is equal to 0.693 over k. The half-life of a first-order reaction is a constant because it depends only on the rate constant and not on the reactant concentration. This point is again worth noting because reactions that are not first order have half-lives that do depend on the concentrations. That is, the amount of time in one half-life changes as the reactant concentration changes for a non-first order reaction. Because the half-life of a first-order reaction is a constant, as we see here in the table, each successive half-life is an equal period of time in which the reactant concentration decreases by a factor of 2. Radioactive decay is an example of a first-order reaction. Earlier in 151, you may have seen isotopes. Many of the isotopes that we looked at were radioactive, as carbon-14 is radioactive. Carbon-14 will decay to nitrogen-14 by emitting a beta particle with a half-life of 5,715 years. Let's look at our example again of carbon-14 forming nitrogen-14. Carbon-14 forming the isotope of nitrogen, nitrogen-14 here. In this case, the decay rate is going to be equal to the number of radioactive nuclei, which we're calling N, in a sample times a first order rate constant called K, which is also called the decay constant anytime we're looking at radioactive decay. This rate law is analogous to the rate law of the first order chemical reaction, as can be seen by replacing the chemical reactant concentration A with the number of radioactive nuclei N. Consequently, the integrated rate law for radioactive decay and the relationship between the half-life and the decay constants are also analogous to the equations that we saw earlier for a first-order chemical reaction. So the integrated rate law for radioactive decay becomes natural log of N over time over N, or the initial nuclei, which is equal to minus KT. In second-order reactions, we see one whose rate depends either on the concentration of a single reactant, raised to the second power, or on the concentration of two different reactants, each raised to the first power. Using calculus, you see that it's possible to convert the rate law to the integrated rate law here, with 1 over A sub T is equal to KT plus 1 over the initial concentration of A. If you need to look at the derivation, it's in Appendix A5. And again, you see that it's in the same format of Y is equal to mx plus B. Looking at this worked example 12.12 there, where you're trying to determine the reaction order graphically, you can ask yourself a couple questions by looking at this data here. One, is the reaction first order or second order? You can also ask yourself, what is the value of the rate constant? What is the concentration of NO2 at T is equal to 20 minutes? What is the half-life of the reaction when the initial concentration of NO2 is equal to 6 times 10 to the minus 3? Or when the half-life, or what is the half-life when the concentration of NO2, the initial concentration of NO2, is 3 times 10 to the minus 3 molar. All of these can be answered simply by looking at this table here. You can refer back to page 465 to look at the answers of this. So it states on this problem on 465 that to determine whether the reaction's first order or second order, you need to calculate the values of natural log NO2 and 1 over the concentration of NO2, and then graph these values versus time. And so that's what it looks like when you graph all that data. So the plot of natural log NO2 versus time is curved, but the plot of 1 over the concentration of NO2 versus time is a straight line. The reaction is therefore second order in NO2. To get a summary of what the graphs would look like, look at table 12.4, where it gives you the characteristic of first and second order reactions, and learn those graphs. Learn what it takes for it to become a linear graph in particular. To calculate the rate constant, we know that it's equal to the slope of the straight line in the plot of 1 over the concentration of the nitrogen dioxide versus time, which we can estimate from the coordinates of the 2 widely separated points on the line. And so that's where come up with this data that you see for part B, and that is the slope. So the half-life of the second order reaction when the initial concentration of NO2 is 6 times 10 to the minus 3 can be calculated from the rate constant and the initial concentration, which is basically 1 over K times the initial concentration of NO2. Again, look on page 466 to see these calculations in depth. Learn the characteristics of both first and second order reactions, both how to calculate the rate, how to calculate the slope, and how to calculate the half-life. For a zeroth order reaction, the rate is completely independent of the concentration of the reactant. And the way to show that is the concentration of A sub T is equal to minus KT plus the concentration of the initial A. So you might ask yourself, when would you ever have a reaction that's not dependent on the concentration of your reactant? Well, the example they give in the book is ammonia in the presence of platinum catalyst can form nitrogen and hydrogen gas. However, you could have a ton of ammonia, but without the platinum, the reaction is not going to proceed. And so only a very small number of ammonias are actually brought to the surface with the catalyst. And so it's not dependent on having a lot of ammonia, but rather just having it associated with the catalyst itself. So now we're on 12.9, which is our third part of this chapter, where we're looking at reaction rates and temperature. Now we all probably agree that increasing temperature is going to increase the rate of reaction. When you think about food being left out in the heat, it's going to definitely spoil a lot faster. As a rule of thumb, reaction rates tend to double when the temperature is increased by 10 degrees Celsius. So let's look at that as it pertains to collision theory and Arrhenius equation. So another example of how temperature affects a reaction would be the example shown in the book here with magnesium being inert in cold water, showing it being blue, but it reacts with hot water, and in this case it turns purple. So this is an example that's given on page 468. So you probably saw this in 151, but if you didn't, we see here the potential energy profile for reaction, in this case A plus BC, forming AB plus C. And we see that as the reaction progresses, the kinetic energy of the reactants is first converted into a potential energy of the transition state and is then transformed into kinetic energy of the products. You see the activation energy being the distance from the reactant to the transition state, and then the amount of heat that's given off. In this case, shown as delta E, showing that it's a exothermic reaction, which would be normally shown with a negative charge. So we talk about this a little bit more, collision theory, in the lecture guide, but as it shows here, you have a plot of the fraction of collisions with a particular energy at two different temperatures. So you see here that the fraction of collisions with an energy equal to or greater than the activation energy, E sub A, is represented here at two different temperatures by the areas under the curves on the right of E sub A. When E sub A is large compared to RT, the fraction, which we're calling F, is going to be approximated by a particular equation, which we'll see shortly. R is going to be the gas constant, which this book uses 8.314 joules per Kelvin mole, and the temperature is always going to be shown in Kelvin. And so from that equation, we can deduce the Arrhenius equation, again, which is shown below here. K is the rate constant. P here is representing the fraction of collisions with the proper orientation for the reaction to actually occur. Z is the collision frequency. We have E sub A as the activation energy, as we've seen before, R being the gas constant, and the temperature being expressed in Kelvin as capital T. And you have the fraction of collisions with sufficient energy for the reaction, showing it as we saw earlier. Again, you can look through this if you want to be able to deduce this formula. It's on page 471. This equation is called the Arrhenius equation, and it's named after Svante Arrhenius back in 1889. So taking the natural log of both sides of the Arrhenius equation, we obtain the logarithmic form of the Arrhenius equation. This equation can be rearranged into the form y equals mx plus b. So a graph of natural log k versus 1 over t is called the Arrhenius plot, gives a straight line with a slope of m being equal to minus e sub a over r, and intercept b being equal to natural log a. The experimental value of the activation energy can be determined from the slope of the straight line. Still another form of the Arrhenius equation, which you see on the right here, basically can be derived, that allows us to estimate the activation energy from the rate constants at just two temperatures. So doing it from two temperatures would give us a new formula, which is not listed here in the PowerPoint, but it is on page 472. Natural log of K2 over K1 is equal to minus the activation energy over R times 1 over T2 minus 1 over T1. So that will allow you to calculate E sub A, in this case in kilojoules per mole. So there's a worked example on the bottom of 472 called 12.13, where it's giving you the rate constant for the gas phase decomposition of hydrogen iodide, and it's giving you the values that you see here. So it's asking for the activation energy. So I would definitely refer to page 473 in calculating that one. Now it is necessary to draw the plot in order to get the linear line for natural log K versus 1 over temperature, and that will be our next slide. And here we have it. So the slope of the straight line plot can be determined from the coordinates of any two widely separated points on the line. So you can get the slope of the line being equal to the change of y over the change of x. And that will allow you to calculate the activation energy from the slope. Again, refer to page 473 for the actual mathematics. The fourth part of this chapter pertains to reaction mechanisms, which we look at in depth in organic chemistry. So this is now on 12.11, where we talk about basically the sequence of reaction steps that are going to describe the pathway from reactants to products. So a single step in a reaction mechanism is called an elementary reaction or an elementary step. To look at the distinction for this, we could look at something like NO2 plus CO yields NO plus CO2 as the overall reaction. Experimental evidence suggests that this reaction is actually occurring through a two-step mechanism. So in the first elementary step, you have two nitrogen dioxide molecules colliding with enough energy to break a NO bond and form another, resulting in the transfer of an oxygen atom from one NO2 molecule to the other. But in the second step, you have nitrogen trioxide molecule forming in the first step as it collides with a carbon monoxide molecule, and the transfer of an oxygen atom from NO3 to CO, yielding an NO2 molecule and a carbon dioxide. So the elementary reaction is basically describing an individual molecular event, whereas the overall reaction is going to describe the reaction stoichiometry. The reactive intermediate basically is formed in one step and therefore consumed in a subsequent step. So they don't ever appear in the overall reaction. So elementary reactions are classified on the basis of their molecularity, or the number of molecules or atoms on the reactant side of the chemical equation. A unimolecular reaction is going to be an elementary reaction that involves a single reactant molecule. For example, in our example here, we see ozone yielding oxygen plus oxygen. A bimolecular reaction is an elementary reaction that results from an energetic collision between two reactant atoms or molecules. In the upper atmosphere, you can see something like this occurring with ozone molecule reacting with an oxygen atom to give you two oxygen molecules. And a termolecular reaction is going to happen when you basically have three atoms or molecules coming together, and this is pretty rare. So again, you could think of something like, playing pool. If you're hitting three balls at once, it's not going to be as common as maybe hitting two or simply one. The rate laws for an elementary reaction follows directly from its molecularity because an elementary reaction is an individual molecular event. So the concentration of each reactant in an elementary reaction appears in the rate law with an exponent equal to its coefficient in the chemical equation for the elementary reaction. For example, if you're looking at the unimolecular decomposition of ozone, you're going to have O3 forming O2 plus oxygen. The number of moles of ozone per liter that decompose per unit time is going to be directly proportional to the molar concentration of the ozone itself. And so here we have a summary of the rate laws for elementary reactions. Note that the overall reaction order for an elementary reaction always equals its molecularity. It's easy when we look at the rate determining step by looking at which one is actually affecting the overall reaction, the faster step or the slower step. So in our little picture here, we see which is more likely to slow down the line, picking up a beverage or waiting for a well-done hamburger. So obviously the slower step becomes the rate determining step in any multi-step reaction. So the way we look at this is that the rate determining step is kind of like the bottleneck, which is preventing the reaction from actually occurring, at a faster rate. So in this example here, we see the first step in the mechanism is slower and rate determining, whereas the second step is going to occur much faster. So we have here K1 and K2 representing both of the initial reactions. They're written above the arrows, as you see, and they are both considered the rate constants for each of the elementary reactions, but the rate of the overall reaction is determined by the rate of the first slower step. In the second step, the unstable intermediate, which is your NO3, reacts as soon as it is being formed. Here we have a multi-step reaction. In contrast to the reactions which the first step is slow and rate determining, the following three-step mechanism has been proposed for the reaction of nitric oxide with hydrogen. In the first step you see is fast and reversible, produces a small concentration of the stable intermediate, N2O2. This intermediate then is going to decompose rapidly to NO in the reverse of the first reaction and reacts only slowly with the hydrogen gas in the second step, yielding a second intermediate, the N2O. The second step, however, you see is the rate determining step. And by the third step, you see that the N2O is going to react rapidly with hydrogen molecule to give you the nitrogen gas and water. So summing the three elementary steps, both intermediates cancel and you end up with the balanced equation for the overall reaction. So here you see that the first step is reversible. We assume that the forward and reverse rates are equal. And finally, we show the final reaction rate. So if you're kind of curious how things are done, then look at the procedures used in studying reaction mechanisms. So first, the rate law is going to be determined experimentally. Then you have a series of elementary steps which are proposed, and then the rate law is predicted by the proposed mechanism. If the observed and the predicted rate laws do not agree, the mechanism must be discarded and another one must be devised. If the observed and predicted rate laws do agree, the proposed mechanism becomes plausible. And plausible, again, is not the same thing as correct. So what we see, especially in organic, is we see several different reactions, and their mechanisms kind of get updated, usually by studying that particular reaction more and more. So you might have like two different textbooks that actually go through different mechanisms for it. The case for a particular mechanism is usually strengthened considerably if a reaction intermediate can be isolated or if an unstable intermediate can be detected. It's easy to disprove a mechanism, but it's seldom possible to finally prove a mechanism because there may be an alternative reaction pathway, which is not yet imagined, that also fits the experimental facts. The best we can do to establish a mechanism is to accumulate a convincing body of experimental evidence that supports it. If you read at the bottom of 481 with me, it says proving a reaction mechanism is more like proving a case in a court of law than like proving a theorem in mathematics. I thought that was very well written. The last thing we're going to look at in this chapter are reaction catalysts. So reaction rates are affected not only by reaction concentrations and temperatures, by the presence of a catalyst. We know some reactions won't even go if you don't have a catalyst. We think of biological catalysts being like enzymes in the body, increasing the rate of reaction so much that the system can actually keep itself alive. So here we have an example of the iodide ion catalyzing the decomposition of aqueous hydrogen peroxide to yield oxygen gas and water. So one of the definitions of a catalyst that you might see is that it can be regenerated, can be used and regenerated, and usually at the very end. The catalyst remains unchanged. Since the catalyst is used in the rate determining step, it is used in the rate law as well. Notice that the presence of the catalyst does increase the activation energy, but does not affect the energy difference between the reactants and the products. Read on section 1215 on homogeneous and heterogeneous catalysts. These are not required on the test, but you might still want to look through it. Catalysts are basically classified as being either homogeneous or heterogeneous. Homogeneous catalyst is one that exists in the same phase as the reactants, whereas a heterogeneous catalyst is one that exists in a different phase from that of the reactants. And so there are several different examples on 1219, which is basically the proposed mechanism for the catalytic hydrogenation of ethylene on a metal surface. And it shows how this reaction actually would not even occur without the catalyst in there, but the catalyst actually provides a surface for the hydrogen bonds to break and to actually form ethane in this case. So that is on the next slide, and that basically completes it. We also think of, obviously with catalysts, we think of catalytic converters as well, and so that's our final slide. I hope this helps, and I hope the lecture guide helps you as well. Thank you.